And we'll move on to our second keynote for today, which is Professor Viktor Jirsa. And so I have not yet had the pleasure of meeting Viktor, but we have heard a lot about his work over the last sort of couple of days in these sort of symposia that we've been having. So, so Viktor is a professor and director of the Institute of Systems Neuroscience in Marseille, France. He's also one of the lead scientists in the Human Brain Project and the Virtual Brain. So I'll hand it over to you, Viktor, where you will be giving the talk on sort of synergies in the brain. So over to you.
Thank you, Faisal, for this very nice introduction. Yeah. Hello, everyone. Good afternoon, good evening, good morning, depending on where you are. Today is the third day. On day one, we kicked off this event with a symposium, with a Roy John Memorial Symposium. And Roy John, he was born on the 14th of August in 1924. And this is, so he would have celebrated his 100th birthday this year in August. And this day is linked to another particular event of a grand pioneer in science and in neurosciences. And actually, it is a day of which very recently, a few weeks ago, Professor Dr. Hermann Haken passed away. Yeah? And I exchanged with Pedro about this topic. All of us were good friends, students, colleagues of Hermann. So I would like to angle today's presentation actually from the perspective of Hermann Haken and some of the contributions that he made leading to neuroscience. He turned 97 years old. This is a very remarkable life, a long life, very rich with many contributions that he has made to sciences. As a scientist in the 60s, he was very renowned to his contributions to laser theory. So the first lasers were experimentally developed in the 60s, and he was the one that actually was contributing a detailed understanding, fully quantum mechanical and semi-quantum mechanical, a classical description of the laser theory, made major contributions to group theory and quantum field theory in solids. In this field, he has also written major textbooks that are still nowadays leading textbooks worldwide being used, in particular solid state. In the 70s, he has recognized that some of the principles that he was using, in particular nonlinear dynamics, bifurcation theory, that many of these principles in solid state could be interpreted as basic principles of self-organization, of open non-equilibrium systems. That led to the development of the field of synergetics, an interdisciplinary field that has led to contributions in biology, chemistry, psychiatry, psychology, and definitely also neurosciences. And one of the key contributions there was that a formal framework has been provided, allowing us to understand the spatio-temporal pattern formation in complex systems. I had the honor and pleasure to be one of his last PhD students and work with him, translating some of these insights and principles into the field of biology and to brain science in particular. Here on the left-hand side, you see a Nachruf, we call it, so an obituary that has been written by one of his students and disciples, and he has been active until the last decades of his life. Some of the pictures at the events where he has participated in 2007 in Germany in Bad Honnef, the Deutsche Physikalische Gesellschaft, or in Delmenhorst 2012. You see him represented here, giving lectures the last 10 years of his life more online, because he was not that mobile anymore. I was happy to be able to receive him here in Marseille, where he was able to give a large lecture about the contributions of synergetics to movement and neurosciences. This paper here I wish to highlight. This is in the mid-70s. It was written from the perspective of physics. However, all the mathematical and formal tools are already there, with the possibility to translate them into other domains. Yeah, there are, I don't even remember anymore, 70, 80, 90 pages, something like this, published in Reviews of Modern Physics. I highly recommend it. The key principles are represented there. This was the key publication establishing the field of synergetics. Imagine you have a nonlinear field composed of many different components, microscopic components that are being described by microscopic equations, typically nonlinear, typically differential equations. These components are nonlinearly interacting, and they are driven outside of the thermal equilibrium, hence it is an open system, by flow from energy, in the case of the laser, mass, or information in terms of social systems. Yeah? This is driving the system out of the equilibrium. Typically, it's controlled by non-specific parameters. So it's not a specific control theoretical orchestration. On the contrary, it's non-specific because it's just temperature gradients that then lead to the formation through certain self-organization principles of patterns, spatiotemporal patterns that are low dimensional and start enslaving all the other degrees of freedom. Typically, the high dimensional systems are 10 to 8, 10 to 9, 10 to 11 degrees of freedom, like in the human brain. And the emergent dynamics is very, very low dimensional. Here you see a simulation coming from an example from the formation of convection rolls, and where you have under temporal gradient where of a bowl, of a dish with a fluid heated from below, you have the formation of these roll patterns that is following the Navier-Stokes equations, and that underlies, for instance, the pattern formation of cloud patterns as we see it often in everyday life. And these structures are the emergent order parameters, collective variables that then enslave, so reduce the complexity of the system and enslave the other degrees of freedom. This type of dynamics was formalized in a mathematical framework. Another student of Hermann Haken, Arne Wunderlin, has put this in a more recent publication, more recent than the 1975 publication, and condensed this on a few pages in this paper here that I'm citing, generalized Ginzburg-Landau equations. And the key mechanism there is a center manifold theorem that actually reduces the degrees of freedom, allows to understand the compression of information. One key element there is that it's the interactions, the nonlinear interactions between the elements are translationally invariant. In the brain, in terms of the connectivity, what that would mean is that the system, every neuron sees the same connectivity as every other neuron does. This is not the case in the brain. Yeah? And this is something that is fundamentally different to all systems in physics that we are dealing with, yeah, that this interaction pattern is not translationally invariant. This has led actually to a development where Hermann and I were working together on contributions, and this was mid-90s, of developing, characterizing the connectivity, leading to this type of Ginzburg-Landau-like equations that allow the application of synergetic principles thereof. Yeah, and you see an example here essentially, this is what we were encountering. And these are some figures from these old papers in the 90s. So these are scans that when later were then digitized and became deep PDF files, but the original was only in print publications. The essence is the following. If you have a two-dimensional sheet, cortical sheet, think of this, you have nearest neighbor interactions, intracortical, but you have fibers that leave the cortical sheet, cortical, yeah, that are singular fibers that have a very particular topology, yeah, and mathematically the way this translates, yeah, is into interaction patterns that follow the same principles as in synergetics, but encounter a different mathematics. So the first part that you see here on the left-hand side, the differential equations, can think of psi as being the neural activity, dot, the time derivative, x, the location somewhere on the sheet. Then this is neural mass dynamics or neural population dynamics locally at the same location. Then you have the locally the nearest neighbor interactions within the sheet. So that would be intracortical interactions that can be described probabilistically, and the connection strength decays over the distance. But then running into the large scale projections, yeah, they are not depending only on the distance, but they are depending specifically on the connectivity. This is not something we know from physics. This particular extension here actually requested the existence of a reformulation of the type of equations as we have them in synergetics. And that has been in the mathematical literature is referred to as the Jirsa-Harkin equation and has been discussed in differential form and in integral form. Let me give you an example. Yeah, this can actually be simulated. If we cut this here along this axis, you see this represented here. And this two-point connection, so this cortical-cortical connection that you see here, within you have nearest neighbor connections, and when I click on it, this will evolve and become a spatiotemporal simulation, and then we will change either the time delay or equivalently the distance of this two-point connection. So here the simulation evolves, a stationary pattern is happening, and now watch out, the distance will become longer, and only the distance is changing equivalent to the time delay, and the spatiotemporal pattern formation changes completely. Now it changed again, reorganizing itself, even though the topology stayed completely the same, the different spatiotemporal patterns are occurring and forming systematically. This can be treated mathematically. Yeah. And the simulation I just showed you is plotted here. This was the first regime, longer distance of the two-point connection, and then even longer. So different spatiotemporal patterns can be studied systematically and provides us then, on the top right, you see a parameter space. It provides us with parameter spaces that are linked on the one hand side to the emergence, vertically emergent stationary spatial pattern, and horizontally on the distance or time delay of the connectivity, in this case, the large-scale connectivity. Recognize large-scale connectivity, in this case, was only one fiber track, two-point connection, but it was also the mid-90s, yeah? And you see that under different parameter regimes, here you, for instance, have everything is black, so no activity can be supported and sustained. Here you have oscillatory activity spatiotemporally with waves, and it changes. So it serves the connection topology serves, not topology, connectivity serves as a bifurcation parameter, as a control parameter, as Hermann Harkin said it. Later, today, almost 30 years later, we're not dealing with individual connections, but we are dealing with sets of connections, of two-point connections, that complete set of all possible white matter connections on the macroscopic level. Today we call this a connectome. Yeah, as you see represented here, data from Cyril Poupon allowing us to go on the resolution of 200 micrometer actually. But I wish to cite out of this paper here from the mid-90s, heterogeneous fiber tracts, so these white matter connections, that connect the cortical, subcortical, and spinal subsystems involved in coordination tasks still have to be implemented in the platform, so the mathematical framework. But it was asking that in the near future, developing technologies such as DTI promise to provide complete information of the white matter tracts in the connectivity matrix of individual subjects. And that was actually a request, because in these papers, in collaboration with Hermann Haken, we have actually demonstrated that the topology, there are steep fundamental properties in terms of symmetry, that the white matter tract needs to be integrated, otherwise large-scale dynamics cannot be understood. Yeah? This is the framework, the theoretical mindset I ask you to have when we actually look at some of the things that have then developed over the past 3 decades, starting in the mid-90s with the provision of imaging techniques that allows us to address these 2-point connections, furnish us with data sets, which gave rise to an enormous to an emergence of enormous activity in the field of brain connectivity. Graph theory entered into the neuroscience. The connectome was named as an entity and became omnipresent in our field. And together with emergent new computational power, the data analysis, high performance computation and modeling became possible to make use of this type of data. Yeah, Human Brain Project is one example thereof, where these elements were all integrated into a platform, then giving rise to the European digital neuroscience infrastructure, eBrains, that we have today. One other key element that is actually important is, and keep in mind that, keep this in mind in the framework of the simulations that I just showed you, where you vary individual, you don't change the topology, but you vary parameters of the connectivity or of the connectome, yeah, that this variability matters. And with the increasing power of AI methods, in particular Bayesian inference, it became possible to build patient-specific brain models, yeah, that take advantage of this connectivity connectome in order to build what we call today virtual brain twins or digital brain twins, depending on from what perspective you come. But bottom line is, this is one of the essential pillars for personalized medicine. And what I want to do in the remaining time is essentially show you some of the operating principles. This I do very quickly, of the what we call a virtual brain, but then applied to one domain, in this case, epilepsy. Operating principles, there are 3 of building this type of model structure on the macroscopic level. I was not talking about individual neurons, but I was talking about populations. Populations, another term is neural masses. Walter Freeman called it a neural mass. And essentially, these are low-dimensional mathematical entities, typically the...
Allez, hop. Merci. Je cherche de télécharger en même temps. Écoute,
Professor Jirsa, we seem to have lost your audio, or it may well just be for me, but I cannot hear you anymore.
Yeah, I apologize, and I have a suspicion of why this happened. Can you hear me now?
Yes, we can hear you now.
Can you hear me now? Just a second, please.
Mm-hmm.
Can you hear me?
Yes, we can hear you now. Yes.
Excellent. Thank you. I'm at home. It's Sunday here, and I have the suspicion that my son connected his headphone, yeah, to my computer here. Sorry. Yeah. Okay.
Yeah,
I continue.
no problem. No problem at all. Yeah.
Yeah, thank you. So, voila. Okay. So neural masses, network nodes, So we are not talking about individual neurons, but populations of neurons. Yeah. So that's the first key element. And there has been lots of activity in the Human Brain Project on this. Second key element is the source to sensor mapping. Yeah. And what that means is when we construct the virtual brain, you see a parcellation here. We build a network out of this. We equip every single network node with the reduced population dynamics that becomes the local dynamics in the equations of the synergetic system I showed you in the beginning. Then we need to connect it with a connectome. Yeah. So build the network. But what is one of the important elements to bridge to the clinic is actually that you can span the network in three-dimensional space in the brain, and then you map it on sensor data. Here, in epilepsy, for instance, on the SEG, or fMRI, MEG, etc. Yeah? So these are the three key elements. Yeah? Neural masses, connectivity, so patient-specific, subject-specific connectivity, and source-to-sensor mapping. In epilepsy, there is one key issue, and in particular in drug-resistant epilepsy, and that is the following. A third of all patients that suffer from epilepsy are drug-resistant. That means they have to be treated in a different way, and a common intervention is actually epilepsy surgery. And for this, you need to know where the epileptogenic zone is located. Yeah? And the epileptogenic zone in particular needs to be explored. And for this, we perform invasive explorations using stereotactic EEG. Yeah? Once the epileptogenic zone, so you see some SEG data represented here, this Jean Banco and Jean Talarac that have developed the technique in the 60s. Yeah? So an EEG electrode is about 10 centimeters long. You see it here. This is a CT, effectively. And there are contacts, SEG contacts along the electrode. Yeah? And with this, you have to interpret this type of data in order to get an insight where the epileptogenic zone is, that then becomes the target of the surgery. Yeah, surgery success is about 60 to 70%, and so that means 30 to 40% failures, and this has not changed over the past 50 years. Yeah? So there are issues, there are big issues with regard to this. How can we help? We are building today high-resolution virtual brains. You see a representation here of a connectome. There we get down on individual subjects. We can go down to the millimeter resolution level. Here you see connectome represented. Left hemisphere, right hemisphere, interhemispheric connections, cerebellum and subcortical areas. Yeah, so this is what it looks like, and with this we essentially, like the field, the neural field I showed you earlier. Yeah, we built this with vertices. Classic numbers for us nowadays are 200,000 vertices, gives us a resolution of 2 to 3 millimeters. Yeah, here you see an example where we unfold the cortex and actually fold into the hippocampus. You see nicely how it rolls here. In this, look at the colors here. So here we go into the hippocampus. For better visualization, you can actually inflate the structure and map it upon a sphere. And that allows us then to perform this type of simulations. It's the same colors I just showed you. This is the hippocampus. We increase the epileptogenicity in the hippocampus. And first, discharges start, actually discharging very fast, classic fast epileptogenic epileptoform discharges, and then it starts traveling. And look at the wavefront propagation. This is also classically known. So these are simulations, yeah, in the virtual brain towards the front. And then it starts recruiting other areas. And at some point it stops propagating. And this is by Kathy Chabon, for instance, was called the inhibitory veto, resulting in a seizure stop. Yeah, this was very local. Now we can actually look at this in a larger scale area. Here's the rhinal cortex, the fibers that come from the rhinal cortex, vertex connectivity. We increase the epileptogenic zone here. And again, I'll show you a simulation. There's a rhinal cortex is here. You will see how the onset occurs. And please look at this area here. This was not, did you see how activity came up? It was not activity that propagated through, but there was a connection underneath, the 2-point connection propagating over and again, providing the same type of activity. This is some phenomenon that can be only described in the context of mixing local and heterogeneous connections, so that are not translationally variant. Then we can put it into the context of the virtual brain. We fold it in 3-dimensional physical space. From the patient, from the CT, we co-register the SEEG implanted and then run the simulations here in the individual parcels. We're putting the energy in red as the activity propagates through the network. And what I'm plotting here on the bottom are the SEEG data as are being measured here by the yellow SEEG electrode contacts that are very, very specific for this particular patient. Here on the right-hand side, right hemisphere, left hemisphere, this is a type of events that you see how the seizure propagates through the network. You see it on the source level, the red balls, red spheres, and also on the SEEG level, discharging and then seizure offset. This is the type of capacities that we have today. What we can do is actually now put it in the context of a workflow in order to help to identify, for instance, the epileptogenic zone. Yeah? For this, we build based on the brain imaging data, individual brains, co-register and fuse the different modalities, yeah, and then estimate the parameters by putting functional data in there, typically performing Bayesian inference, different techniques, MCMC techniques or SVI we use nowadays quite a lot. So generally different variations of Monte Carlo techniques in order to estimate posterior probability distributions of the parameters, because the model parameters are the interface between the data on the one hand side and the model on the other hand. Yeah, this is how we communicate with a clinician. Then we reconstruct a patient, we estimate the epileptogenicity across all brain areas. You see posterior probability distribution, and if it's above the red areas, that indicates epileptogenic zone, that we then plot here, for instance, and overlaid with the anatomical MRI. And with the anatomical MRI. So this is what we are passing. Yeah. So this is what we can do today. Just in closing, what I would like to show you is actually what is the added advantage of mixing causal mechanistic models with this type of data analysis techniques using Bayesian inference. The added value is the following. What we start off with in normal diagnostics is you have to make a decision, or the clinician makes a decision for a particular patient based on the history and the EEG, where to implant the electrodes. And then based on this implantation, he or she has to make an estimation of what they think that the epileptogenic zone is, and this will be operated on. Yeah? What we are doing is we are linking this to a virtual brain based on patient's connectome and our understanding of neuroscience translated into mathematical theory and self-organization theories, connectome, connecting individual areas. But we can make statements or get insights about the entire brain. So we have partial sampling of data, but put it in inference framework of the entire brain. That allows us actually to make statements about epileptogenic zones that are outside of the accessible area. So essentially we are unfolding the space. Yeah? Does that make any sense in terms of added value? Does it translate in real world application? The answer is yes. Yeah. So here for 25 retrospective patients, when you look at the correspondence on the horizontal axis with a virtual brain prediction, for seizure-free patients 1 year after surgery, you see actually that the number of patients and the correspondence, when you map the areas that correspond to each other, for seizure-free patients peaks at 100%, but it drops down enormously for not seizure-free patients when there is no correspondence with the prediction that comes from the virtual brain. And actually, this would be already okay, but if you analyze these data here, it turns out that 29% of all surgery failures are linked to this case here, where the clinician did not have access to this knowledge outside of the accessible area. Yeah? That's the way, what I wanted to share with you, and essentially provide you with an understanding that mixing models, our understanding of self-organization with modern neuroimaging data can get us further than pure data analysis alone. Yeah. And today, where we want to go, especially in the context of eBrains, our digital neuroscience infrastructure, we're putting these elements together in order to build frameworks for personalized medicine. Yeah. So I thank my colleagues and friends that have contributed over many, many years to this type of endeavor, and also the funding agencies. Thank you very much for your attention.
Thank you very much, Professor Jirsa. It's a fantastic presentation. I love the narrative going all the way from the tribute to some of the most recent work that you're doing. We're a little bit limited on time, so we have one question and we'll keep it just to that one. So in the chat, we have a message from Rex. Thank you, Rex. So the question is, do you map post-treatment to monitor how the brain reconnects or loses function?
Not in epilepsy, but in stroke recovery. Not me, but colleagues of mine that are looking in terms of stroke recovery. There it's being done. Daniele Marinazzo is, for instance, in Ghent in Belgium, would be a name that is very interested in this type of topic and map connectivity, in particular during recovery. Something that we are very, very interested in, and that connects also to the talk of Steve Luke before. We just started working on psychiatry, in particular schizophrenia. Yeah. And there we are following schizophrenic patients. Yeah. There, the imaging data features that we're using, it is fMRI. We have some experience there, but we cannot address so many different parameters. We would be completely lost, but we are focusing only on medication. Yeah. Questions such as when to change medication and how to change concentration. This is our control parameter. And there we know that some of the spatial dynamics is affected. Will it be identifiable? Will it be predictive? There are some first studies that demonstrate, yeah, this can be the case. And I'm saying this here explicitly because schizophrenia is one of the mechanistic underpinnings is understood to be linked to connectivity, essentially. Loss of synaptic connections. And this is something that we are following, and there we are performing longitudinal studies with Charité and Munich and here in Marseille.